Thank you. Can you hear me?
Yes, we can hear you. Thank you, Patrick.
Awesome. Yep. So, my name is Patrick Shober. So I am presenting some work here that was recently published by my colleagues Oriane and Jeremy. Jeremy was my postdoc supervisor at the Paris Observatory, where I finished up 2 months ago. Um, and currently, I'm working with Paul Abel and Mark Fries at NASA Johnson. But I digress. So following Peter's talk, in this talk, I'll be talking more about, instead of the strengths of small bodies impacting our atmosphere, looking at the orbital distribution and what we can say about if there is statistically significant clustering within that population. In other words, do we see streams of meteorite dropping bodies? As in the last few decades, there have been many claims of linkages between meteorites, fireballs, and near-Earth asteroids. This has been a well-researched issue for the last, I would say, 2-3 decades at least. Next slide, sorry. So for the impact data sets, there have been many claims and many searches, but in my opinion, there's not really anything terribly convincing. There are a few nominal cases where there has been arguments put forward that people have talked about, but in general, there has not been a significant identification of a cluster. Next, please. So in these studies, very, very briefly overviewed, very glossed over, but in most of these studies, they use what we call orbital similarity measures, or d-values, or dissimilarity criterions, or dissimilarity functions, d functions, something with a d in the name, and that's it. The original form of this was proposed by Southworth and Hawkins in 1963, and these d-values compare the orbital elements of particularly different meteors, different fireballs, in order to understand how similar they are. And the original intention there was to really identify meteor showers and body associations. So these d-values and these orbital similarity measures have remained a staple of meteor science, specifically for identifying meteor showers, but they've also been used a lot for trying to identify clusters and then NEA linkages. The main thing that you should think about it is that the smaller the value is, so you have, in order to calculate the d-value, you take the orbital elements from two different fireballs or two different objects, two different orbits, and you get a value. The smaller the value, the closer or more similar they are. Next slide, please. So some major previous notable meteoroid stream searches, or the most notable is probably the Pribram and Neuschwanstein meteorite falls. So there was a very notable paper by Pavel Spreny in 2003, noting that these two meteorite falls had very similar orbits, arguing for a stream. Also, of course, Chelyabinsk and near-Earth asteroid 1999 NC43. And more recently, there have been more and more papers trying to use these d-orbital similarity measures in order to identify parent bodies in near-Earth space. And these are just some examples, they're not all of them, but while working at the Paris Observatory, we were working a lot on looking at the statistical significance of identifying meteor showers within meteor databases. And we saw these several papers, not just these, making very large claims about the percentage of objects that they could link to fireballs and meteors. And there are a few reasons why looking at these studies, but they have a few statistical miscalculations in them, I would say, or bad assumptions, more likely. that inspired us to work on this paper. Next slide, please. So in order to understand how to identify orbital clusters in the space, I'm going to use an analogy, or try to at least. Next, please. I should have probably not put in so many transitions. So I'm going to try to use a golf analogy because I think it's very apparent. Next, please. So let's imagine we're at a golf course, and so instead of asteroids and space, fireballs, and all that, imagine we're going golfing. We hit the ball, and it lands in the middle of the fairway, or all amongst all the grass. Next. And you find the ball laying in the grass. You find it on one particular blade of grass, and the logical fallacy, I would say, that is often, unfortunately, carried out by some of these papers is you look at this ball and you see it on one blade of grass and you say, oh, what is the odds that it would have landed on this blade of grass? Essentially the same question of, we have a fireball. What's the odds that it came from, it's really similar orbit to this asteroid. What's the odds it came from this asteroid? But in this case, in many of these papers, what they do, next please. If maybe one more time. If I think this is next again. Thanks. Yeah. So often in these papers, what they do is they look at all the possibilities, all the possible asteroids. In this case, their way of looking at it would be, oh, there are billions of blades of grass. The odds that landing on this one is 1 in a billion. It's not all the studies that I mentioned, definitely not, but particularly the last ones. But they would look at the region around this blade of grass and say, oh, wow, the odds that we got this close to this particular object or this particular place is really low. But if you click next twice, thanks. So this is obviously not the way to look at the problem. Next again, please. So the problem with this is instead we must assume the null hypothesis is that there are no clusters and everything is sporadically distributed at random. Whenever you're asking what's the probability of getting towards this blade of grass or this asteroid, you're placing some importance on this asteroid that it doesn't really merit. Next, please. And next again, sorry. So instead, what we should be asking is what is the probability of getting this degree of similarity with any asteroid? When you do this, you realize in the golf analogy, when you hit the golf ball, the odds that it's going to land on any blade of grass is going to be 100%, unless you're really bad at golf. So instead, we wanted to re-examine this question of orbital similarity within the fireball population and examine it from this context. Next, please. So what did we do? So we took data from, we examined 35,012 near-Earth objects. We identified over 600 meteorite falls, identified by the European Fireball Network, the Desert Fireball Network, and the French Football Network. We also examined the orbital distribution of 310 USG sensor impacts, and also the 50 meteorite falls that we've recovered with precisely measured orbits. The next important aspect is we calculated the cumulative similarity frequency distribution. So if you're familiar with a cumulative size frequency distribution, it's the same thing, but for similarity. I can explain it more when the plots are on. But we also, most importantly, estimated the degree of similarity expected within the population due to random associations. So if you take the sporadic background and then you randomly draw the same number of objects in your population, what is the degree of similarity? What is this cumulative similarity frequency distribution look like? And then also looking at the dynamical basis of, oh, should these streams even exist from a dynamic aspect, we also estimated the decoherence lifetimes of streams within using 300 fictitious streams and chaos maps of near space. Next, please.
You have 5 minutes.
Okay. Okay, so what did we find? Very quickly, no, but yes. So next, please. So this is that cumulative similarity frequency distribution. On the x-axis, you have the similarity value. In this case, it's DH, but as you go to the left, it's more similar. As you go to the right, it's less. And the number, the y-axis, is the number of pairs within the population, examining all possible combinations, the number of pairs with that similarity or more similar. So the blue region is our 3 sigma region for random associations, and the red is the actual 50 meteorite falls. And as you can see, it falls within the 3 sigma region. So the number of meteorites associated with each other are completely expected due to random associations. And I'll quickly go through a bunch of these. Next. You can see that when we examine the 616 falls observed by the EFN, the DFN, and Frippon, we find the exact same results. Next, please. If we look at meteorite falls versus the near-Earth asteroid population or near-Earth object population, we also find that it's within the 3 sigma region, and we don't find any statistically significant clustering with any NEAs in particular. Next, please. And this is also the same for the 310 US government sensor impacts when compared to near-Earth objects. Next. However, when you get to near-Earth asteroids, and I guess this was perfect timing whenever this came out, because it was only a few months earlier that if you saw the paper by Granvik and Walsh detecting an excess of asteroids on orbits with perihelion near the Earth and Venus, that we have concurrently found that the clustering within the near-Earth asteroid population is consistent with this result, that there is a statistically significant excess of similarity within the population beyond that which is expected from sporadic associations. So that is demonstrated by that kink in the red curve going above the blue region, indicating that there is this excess on very small similarity values as well. Next, please. When we do this, we did a clustering algorithm using a dbScan algorithm, which is a density-based algorithm. And we essentially set it so that it should identify clusters that are corresponding to this excess that you saw in the previous plot. And we find that, without spending too much time, that this excess, these clusters are all concentrated towards Q of 1, which is consistent with the results from the other authors. And next, please. If we look at the decoherence lifetimes based off our integrations, we see that we map near-Earth space. So this is semi-major axis versus eccentricity for 0 inclination orbits. The color is indicative of the decoherence lifetime expected for tidally generated NEA clusters. And we find, if you find where the line corresponds to the Earth, the aphelion perihelion line, you can see that essentially all the fireballs that you would expect to be detected here are, the streams would only have decoherence lifetimes of around 20,000 years or less normally, indicating that it's the minor fraction that we discover, or the lack of discovery in the meteorite dropping data set, and the very minor component we find in the Earth asteroid data set is consistent with a minor mechanism generating this, so this tidal disruption mechanism, and also the very short decoherence times of the streams. That is the time it takes to just blend into the sporadic background. Next, please. And very quickly, this is just a chaos map at 0 inclination, semi-major axis versus eccentricity. And this is basically just to show that in near-Earth space, the Lyapunov lifetimes, which is the color plotted, are only a few hundred years. And in that way, for many of these, some of these papers that just use orbital similarity as a way to connect two bodies, when you only have two objects or one pair, it's orbital d-values, these dissimilarity criterions aren't really made for that. They're made for analyzing large amounts of data and trying to identify clusters, not individual values. And whenever you have chaos in the population like this, a similarity might not physically make sense. Next, please.
And please finish up.
Yeah, I think it's the end. Yeah.
Oh, okay.
If you could just, I think, yeah, there should be 4 of them or something. Yeah. Yeah, so we find about 0.1% of the population. Decoherence lifetimes already mentioned. Yeah, so we find in the meteorite dropping population that there is no evidence, but within the asteroid population, we find clusters. It's just, thank you.